Should we do it?
Sure.
Yeah. Let's get started. People might trickle in. Great.
Okay. So welcome everyone.
Mara's been great.
Yes. So we have two speakers today. We have Mauro and Kate Whitacker here today, so very prestigious guests. So we talked today really about the core of the whole, like the core of the journal club series we were running here. Basically, it's really about the star formation morphology and how the link, the two things link together. And so Mauro, the first speaker, he's very well established in the field, and these people don't have CVs, so it's hard to kind of reconstruct his historic path exactly. So I just want to mention a few things. So he did his PhD at the University of Rome. I know that he was at the Space Telescope for quite some time, and now he's professor at UMass, so about 2 hours west from here. He has done, of course, a lot of very important contributions to the field of galaxy evolution. He has really kind of initiated and led the whole GOODS program, basically, especially with the Hubble Space Telescope. Then he has pioneered the work on nano-membrane galaxies to find really high redshift galaxies, and he and his team really measured the first time the cosmic star formation with density out to redshift 4 or so. And in recent years, he has become more interested to understand how galaxies form and evolve towards low redshifts, in particular mapping out the star formation in the galaxy population, and this is also what he will be talking about today. So he will be really focusing on the link between morphology and star formation. So take it away.
Thanks, Andrew. Thanks for having me. It's very nice to be here on such a beautiful day. And so the link between morphology and star formation. Let's dive into the subject. So I think it's reasonably safe to say that when they form stars, that is galaxies, they look like disks. So star formation and morphology. And the cartoon here is from a paper that discusses the tidal torque theory, which is the theory that we use to explain how galaxies get their angular momentum as the baryons stream in the halos. So why do we say this? Well, I like to cite this particular paper, which I found it interesting, is from this author and his team from the University of Tokyo a few years back. These people downloaded pretty much the whole Hubble Legacy Archive and identified some 200,000 star-forming galaxies at any redshift, selected in a number of ways to study their morphology. And the conclusion of this paper is, it's a long paper, but let me try to summarize it. If you use the Sursich index and the Sursich function, plotted here is the evolution as a function of redshift of the effective radius, the Sursich index, and the specific the surface star formation rate. The result I want you to take home is that the Sursich index, the average Sursich index, tells us that these are disks. It averages at about 1 and a bit, typical of the exponential profile disk. And I will add this because I think it's relevant. If you look at the other diagnostics, like the evolution with redshift of the effective radius, the distribution function of the effective radius itself, all these diagnostics, which the theory predicts to be log normal, are at least broadly, but I would say quantitatively, largely consistent with the prediction of the tidal torque theory, incidentally. When they form stars, they look like disks. And now there are quite a bit of dynamical measures, kinematical measures, rotation velocities, from redshift 0 all the way to 3, although the completeness at any specific redshift is different, that basically support these assertions. They form stars. They look like a disk. Mind you, the disks we see at redshift 3 are not the same disks as we see at redshift 0. They are thicker. There is much more turbulence. But they are velocity dominated. The V over sigma ratio tells us that their dynamics is velocity supported. In the last couple of decades or so, we have learned how to identify both star-forming and non-star-forming, quenched, let's call them this way, galaxies at high redshifts. At any redshifts, we could do the measures with some confidence. The mix of galaxies exhibits a bimodality. When they form stars, they look like disks. When they don't form stars, they look like spheroids. But I put the accent, they look like spheroids, because For example, in this chart here, you do see plotted in a very common diagnostics to distinguish star-forming from non-star-forming galaxies called the UVJ diagram. Color-coded is the Sircich index. So conventional, you can think that Sircich index less than 2.5 speaks of a disk, bigger than that speaks of a spheroid, at least the light profile of a spheroid. And this is for galaxies up to redshift a bit higher than 1. And you do see that when they are disks, when they are blue, which means form stars, they look like disks. When they are not blue, they're red and dead, they look like spheroids. This goes all the way to redshift 4. This is the work of my graduate students, G1G. Similar plot all the way to redshift 4, where photometric techniques, at least, allow you to select candidate passive galaxies. So the question is, do galaxies undergo structural transformation as they change, as they quench, namely as they change their star formation activity? It looks like they do, at least morphologically, which is the heart of our conversation today. Then I would like to attract your attention on another, at least let's put it this way, candidate bimodality. Why I use the quotations here. This result is being debated. I would say that it's safe to say it's not completely established, but I think it's a very interesting result. Let me discuss it. This particular plot is from a recent paper by Reinhard Genzel's team in Munich. Plotted here is the fraction of dark matter in the half-light radius of galaxies versus the rotation velocities. The rotation velocities is actually obtained, there is a coefficient missing here, the K coefficients, but it's essentially a model that takes into account both the contribution to the dynamical supports of rotations and velocity dispersions. So call it a proxy for mass. What you see plotted here is this line here is the best fitting line to redshift 0 early type galaxies. Redshift 0 early type galaxies, ETG, have a relatively low dark matter fraction within their effective radius. These are big, massive bulge disks. Up there, the squares are redshift 0 late type, spiral galaxies. The Milky Way is this one. These two are two averages from redshift zeros as well. The interesting points here are these blue points. These are galaxies for which dynamical measures could be made and the dark matter fraction could be measured, and this includes both the stars and every other, and the gas, baryons, cold phase, hot phase. Well, there is no plasma phase here, but that they could measure. And the interesting results is these are velocity-supported systems. They are thick disk, that is, but they belong to where current early type galaxies belong to. Their dark matter fraction is low, whereas modern disks seem to have a much higher dark matter fraction. This is my estimate for the current cosmological dark matter fractions from the Planck cosmological parameters. So the bimodality is this one. Today, non-star forming galaxies have low dark matter fraction within the effective radius. Star forming, or at least disky galaxies, have higher, a factor of 5 higher. Now, caution. People are still debating the observations. Some people claim that these numbers have been severely underestimated. Some people say, no, they are correct. But I mean, I think if this is confirmed or refused, anyway, it's another interesting correlation, very interesting, because it's structural correlation between star formation and morphology, actually more dynamical structures of galaxies. So the questions. If galaxies really undergo transformations as they quench, essentially the question is, what drives this transformation? Quenching appears to be the big divide between before and after the morphological and potentially the dynamical transformations. And what is the relationship with morphologies? In particular, why do we care if a galaxy changes its star formation, its dynamical and morphological status as it quenches? Well, my answer is because it teaches us what happens to its gravitational potential. So it teaches us the accretion mechanism that this galaxy undergoes, which, since we still don't know exactly what quenches a galaxy, might actually even illustrate what is that switches off the star formations in a galaxy. In particular, today's spheroids have a very low V rotation over sigma parameter, whereas disks have a very high one. How and over which timescales do galaxies get rid of their angular momentum? And if it is related to the change in morphology, maybe it's a consequence of the same changes in the gravitational potential of the galaxy. What do we know about transformations of galaxies, at least at high redshift, as they quench? I'd like to show this plot. This particular one is from the work of my graduate student, Bomi Lee, but there are essentially identical plots obtained by other teams, Mauro et al., my opponent here, Whitacker did beautiful work a couple of years back on the same thing. Concentrate on these two panels are in two different mass ranges, less than 310 to the 10 solar masses, bigger than that. 4 redshift bins plotted here is a proxy for the specific star formation rate. This is essentially the distance from the main sequence of star formation. When a galaxy is forming stars in a normal mode, it sits in here. When it forms stars like crazy for its mass, is here. When it starts to quench, it's down here. When it's red and dead, it's down here. The y-axis shows the projected stellar mass density in the innermost 1 kiloparsec radius. So it's the core stellar density. What you see here is that before a galaxy quench, the dynamic range of its central density is very large. By the time the galaxy is dead, that dynamic range is restricted to high value. The uppermost limit is mass dependent, and it goes, is the higher the galaxy mass, stellar mass is, the higher the density. But essentially, you lose a factor of 4 in logarithmic dynamic range by the time the galaxy changes. So essentially, when galaxy decided they had enough to form stars, they have developed a very dense stellar core, the nugget, as is called by people who work on these things. It's mass dependent. As you can see, a lower mass, there is more scatter, but it is a long story. So this is a direct piece of evidence that we have. This correlation exists at every redshift the same way. The scatter is consistent with our ability to carry out the measures. So this is from another team. Oh, by the way, I should say, color-coded here is the luminosity-weighted stellar age. And you do see very well that, galaxies quench when they are old. And this dynamic compression happens when galaxies are old. This is from the Mauro team. This plot is actually rotated around the diagonal by 90 degrees. So you have to mentally rotate it, but it's essentially the same plot. Same results. The data are somewhat different, but what is interesting is that this happens at every time. So plotted here is not anymore, is again the histogram of the value of sigma 1 in 4 redshift bins, And you see that the behavior is essentially redshift independent. At every redshift happens the same, which has been interpreted as the individual galaxies do the same as they evolve in a way that, at least qualitatively, is mostly mass dependent, but it happens at every epoch. People have been asking lots of questions. Could it be, for example, that spheroids are intrinsically less conducive to maintain a sustained star formation activity? This has been suggested in a number of papers. I think Whitacker has some results as well, Madam Opponent. And but a clear correlation between morphology and star formation, I would say, is on a physical ground, is not yet being established. The loss of angular momentum. So today's spheroids, there are fast rotators and slow rotators for sure, but their V over sigma is much less than the ones of spirals. What is the situation at high redshifts exactly in the aftermath of quenching? Well, the measures are really difficult because we have to do kinematics using absorption features. The galaxies are dead, there are no emission lines, spectroscopy is very, very hard. This is pushing the limits of the largest telescope we have. In fact, this paper is a very recent paper by Andrew Norman et al. these are, I think, Magellan and Keck spectra, 3 galaxies. These are the best cases we could do so far. The galaxies range in redshift between 2 and 2.5. These are passive systems. And plotted here is their ellipticity obtained from, these are lensed galaxies. This is why they could do it. Hubble images after lensing reconstruction. So all the systematics of the lensing reconstructions have to be carefully kept under control. And plotted here is the spin parameter from their rotation curves. They measured rotation velocities up to 375 kilometers per second. And what you see here are essentially redshift 0 galaxies, okay? And as you can see, the high redshift galaxies have a much larger spin parameter for their stellar mass compared to their local redshift counterpart. And these galaxies is in the same range. Those two are really out of, overboard. This one is still in the range of local galaxy, but still on the upper end of the distributions. This is very interesting. So they look like a disk. They look like a spheroids because their central nuggets very likely changes their light profile. They're not disk-looking anymore, but they seem to be rotating, at least these 3. Mind you, it's only these 3 that we know. There are tentative measures, but none of them is conclusive. To the best of my knowledge, and my knowledge might be incomplete, these are 3 cases in which the rotation curve has been really measured carefully. Interesting. So they look like a spheroid, but they rotate. And again, do we call this a result out of 3 galaxies? It's maybe still tentative. Maybe we have not sampled the dispersion or kinematical properties of quenched galaxies at high redshifts. So I asked myself, I don't have access to big telescopes, or at least not easily now. And I asked myself, I have this beautiful HST data. Can I do something to look for other evidences of morphological transformations? So I reflected on the fact that sigma 1, the parameter I showed you before, is not really informative about the whole structure of the galaxy because it teaches us what happens in the core of the galaxy. If galaxies undergo massive dynamical transformations, more structural transformation, this is something that has to involve the whole volume of the galaxy, including the regions where the dark matter gives its dynamical contribution, which is not in the innermost kiloparsec. So which metric to use? Light profiles again? Nah. It's model dependent, it's parametric, there are awful covariances. I just resorted, because I'm lazy and didn't want to think too hard, using the Gini coefficient. What is the Gini coefficient? It is measured within the Petrosian radius. What is it? The Gini coefficient is a parameter, this is the mathematical definition, that measures how unequal the light distribution is in volume elements, think pixels. And if you actually measure the lights at a wavelength that the light is mostly proportional to the mass, is a measure of how the mass is distributed in the galaxy. I also used M20, which is another statistical non-parametric parameter that tells you the amount of lumpiness that the mass distribution has. The beautiful thing is that these involve very large volumes of the galaxies. And if you use the Petrosian radius, you minimize, in theory, you make it insensitive to surface brightness bias. To give you an idea, this is the distribution function of the Petrosian radii of my samples that spans the redshift being from 1.2 all the way to just 3, about 3 and a bit. Petrosian radii distribution goes all the way to fairly large values. If you look at the RE distribution, the effective radius is much, much smaller. In fact, passive galaxies are very small. And sigma 1 is measured in the innermost kiloparsec, so really local. So the idea here is to look at correlations between morphology on large scales and star formation. What did we find? Plotted here, you see the distribution, the histogram in 3 mass range: small mass, less than 6×10 to the 9, intermediate mass from 6×10 to the 9 to 3×10 to the 10, bigger than 3×10 to the 10, all the way to a few units 10 to the 11 solar masses, stellar mass, of Gini and M20 in 4 redshift spin. What you see here is that, especially at the high mass, there is a very pronounced redshift evolution of the Gini coefficient, in the sense that the Gini coefficient gets bigger as the redshift gets lower. What is the meaning of the Gini coefficient getting bigger? It means that as galaxies grow in size and grow in mass, they put more mass in those volume elements that were already richer in mass. They increase the inequality of mass distribution. And this is a mass-dependent effect. It's very pronounced at big mass, it gets less pronounced at small masses. At the same time, the M20 tells us similar evolution. As the redshift gets lower, Gini gets less negative, which means it gets more lumpy. It's increased lumpiness. Okay? This is the cumulative distribution function. We will debate this later. Let me go, even if I omit some details. Now, these, of course, are snapshots at different redshifts, right? This doesn't provide any reassurance that this is the evolution of the individual objects. It could be simply that the population mix is changing as a function of redshifts. To address that issue, we also studied at fixed redshifts in 4 redshift panels, big masses. Let's focus on the big masses first. The distribution of Gini versus a proxy for the star formation activity. And as you can see, even within each redshift mass, its redshift bin, in the high mass bin, the distribution as the galaxy transition from being on the main sequence, sub-main sequence, so star forming, quenching star formation, quenched star formation, the Gini coefficient becomes higher and higher. Their mass distribution becomes more and more unequal. You can have this in 2 ways, in many ways, in fact. You can add some lumps that does the trick. It increases Gini, although we will show in a second that it is not the formation of the nuggets that drives entirely the Gini growth. You can have structure develops by arms, bars. Maybe the whole mass distribution becomes peakier. Maybe you acquire low surface brightness outer regions by accreting satellites. Those are all phenomena that will increase your Gini. Essentially, they increase the inequality of the mass distribution. And this is for the low mass bin. In the low mass bin, there is a bigger dispersion, as noticed before. So this is the test we use to test whether the growth of structure effect could be driven by the growth of the central nugget. The answer is no. We cut the distribution in 2 bins, one with low central distribution, one with low central density, another with high central density, as shown here in the caption, and the same growth is observed. This provides some reassurance that the evolution of Gini is not driven by the well-known fact that as galaxies evolve and quench, they develop the nugget, the central nugget at the center. Another possibility could be that quenched galaxies. Now, before I go on, I have to stress a very important thing. The same phenomenon is observed both in star-forming galaxies, the phenomenon of the growth of Gini, and in quiescent galaxies. If you look at quiescent galaxies, you take, in this particular case, a snapshot. Quiescent galaxies do the same. Now, if star-forming galaxies, which at high redshifts are accreting a lot of gas, the gas fraction is very high, the gas is highly dissipative, the fact that the star-forming galaxies accrete on a fast time scales, they develop the nugget, they certainly increase their baryonic mass because the baryons are so dissipative, is hardly surprising. What is surprising, in my view, is interesting, is the fact that even the quenched galaxies do that. Because quenched galaxies, very likely, they don't do any more dissipative accretion. But if their light profile changes, this says that their gravitational potential changing. Remember, these are big scales. How is that possible? What drives that, right? Of course, if you look at this plot only, you could still have the doubt, but it could be that the passive galaxies do this, not because they do evolve, but because of the addition of Frenchly quenched former star-forming galaxies, which do it, and for which you don't find any problem. Well, we think maybe this is not the case. We did a test of following galaxies at progressively lower quenched galaxies at progressively lower redshifts, but including only the galaxies whose stellar age is such that they have quenched prior a fixed redshift, in this particular case 3. This test is noisy because it depends on your ability to measure stellar ages, which are a difficult measure. But, this is what we could do. And basically what we found is that no, the effect is still there. The effect is still there even if you simply follow the oldest galaxies at any given redshift, so that you basically filter away the freshly added, quenched one. So let me briefly say something which I think is relevant to this very audience. To understand what was going on, we asked for help the illustrious TNG 100 simulations, which is remarkable. It does reproduce many of the observed properties of the galaxies, including the pistol diagram, specific star formation rate versus central density thing. The main features of galaxies that we are interested in seem to be reproduced, captured by the simulations. Well, the same evolutions of the genie is observed in the illustrious galaxies, at least at the semi-quantitative level. I will skip the details, but you do see the same. And plotted here is, the M20, the Gini. What is very interesting is that with the simulations, you can go and measure the Gini coefficients of the dark matter too, which lo and behold, it does the same. The dark matter halo follows what the other non-dissipative component, the stars, do. But the interesting part is, if you rerun the simulations without the baryons, the halos don't do it, which tells us that what we are seeing is actually baryonic, is an effect of baryonic physics. All right. I think I'll stop here and I'll give my opponent her time. What does this mean physically? Physically probably means that you're seeing changes in the gravitational potential. How do you connect it with the physics of the galaxy? This is work in progress, but the nice thing about the Gini is that basically it's a density. And if you study the derivative of the Gini coefficient, you use Poisson equation on the density, and you commute the derivative of time with the Laplacian operator, and essentially you study temperature variation, the content of, and you can use the heat equation to derive to understand the injection of energy in the interstellar medium. The energies are very large. Calculations done by people, we're talking of 10 to the 60 ergs for you to enjoy from in a halo of 10 to the 12 solar masses from redshift 2 to 1. There's plenty of energy there to do the quenching, to do the transformation, and so forth. But this is work in progress, this is the future. Let me stop here. And I hope I gave you a hint, a taste of the fact that maybe there is evidence that I have formal conclusions right here. But let me put them on, and when I speak, you read them. I think that there is evidence that, yes, galaxies do undergo structural transformation, but it's more complicated than we think. It's not that they are disks as they form stars and they become spheroids as elliptical galaxies today. They certainly change their structure, they change their size, they change their light distributions. The change of their dynamics is TBD, is very uncertain today, but it looks complicated. It's not that they lose their angular momentum like this just because they quench. I'll stop here and I'll wait until the end of Kate's presentations to continue with the debate.
Thank you, Mauro. We have time for one clarification question, and afterwards, we will have more general questions after. Or is there any clarification question for this talk? More general questions we will have at the end. Yeah.
I guess my simple clarification question would be, I'm looking at some of these plots, and there are enough data points that you make some conclusions about, I think that the gene coefficient means that there's the growth of these lumps instead. Like, I'm guessing if you look at actual images, that agrees with your intuition. Like, what are the pictures of some of these galaxies look like? I didn't really see any of those during the talk.
So you're asking whether, if you look at galaxies, you do see their morphology consistent with the growth in Gini?
That's right.
Well, galaxies do look more structured as they evolve, right? Interestingly, systematics effect, if this is what you're thinking, go the opposite way. If you have more resolutions, you should see more details, and so Gini, in fact, especially. You reveal more parts of the galaxies, right? Gini should go down if they were more diffused. It goes the opposite way. But galaxies do acquire more structure that is consistent with the growth in Gini. Although I can't do Genie on the fly just looking at the galaxy, but yeah.
Okay, let's thank Mauro again. And
And this. And
Oh,
this.
I have one.
And this.
Okay, most of you say that. So it is my great pleasure to welcome Kate Whitacker to the CFA. Kate is a professor at the University of Connecticut. She is recently the winner of a Sloan Foundation Fellowship, which is very fancy and prestigious. It means she's very
How do I turn
smart.
this on?
So we're very lucky to have her here
this one.
today. Kate was a PhD student at Yale University with a number of us here, and we were all very grateful to get to work with her. She was a shining star of Yale University. She got a thesis prize for some really pioneering work on this huge and very innovative photometric survey, and some of the first and state-of-the-art constraints on the stellar populations and redshifts of high redshift galaxies. She was then a Hubble Fellow at UMass Amherst, and she, as I mentioned, is now at UConn. And she's really an expert in all aspects of the topic that we're covering this semester, the structure of galaxies, their morphologies. She's one of the world experts in measuring this stuff, measuring photometry and spectral energy distributions of galaxies, and then turning those into stellar population properties. So we're very fortunate to have Kate here today. Thanks, Kate.
Thanks. Thank you, Erica. You guys hear me? That just doesn't sound, okay. Awesome. That was a lovely, I think one of the nicest introductions I think I've ever had. So thank you. I'm really excited to be here and battle my opponent, I think that's the word we use, my opponent, Professor Giavalisco, in this Battlestar Galactica, however we say that. Right. So I thought that I would, in all of the nice stuff that Mauro talked about and a lot of observations, I thought I'd try to mostly pick up where he left off and then try to think a little bit more in terms of questions of where we are now, where we can be in the short term, and then also look a little bit forward into the future in terms of what do we need to start to understand this connection between morphology and star formation. And hopefully I'll try to sort of come back to some of the excellent points and stuff that you showed, Mauro. So, you know, if we think about our census of the universe, I would say that our understanding has evolved a lot in the last decade or two. And it should be worth noting that we have, when we make diagrams like this that show the cosmic star formation rate history over most of cosmic time, a lot of this is because of initiatives like what Mauro led with GOODS and having these deep, broad wavelength extragalactic surveys to understand and get a great census. And so we now really have a great census of when star formation was occurring with the peak at cosmic noon. This also happens to be the peak of black hole, supermassive black hole activity around a similar epoch in our universe. And then this is also where the most massive galaxies are really rapidly shutting down, and something is stopping their star formation around roughly cosmic noon. And you can see here, so the quench fraction, if we look at about 50%, that happens around redshift of 2, when you start to be dominated on the massive end, so say 10 to the 11. Most galaxies are quiescent below a redshift of 2 for high mass galaxies. That means that all the action is occurring either at cosmic noon or earlier. And so I think a lot of the things that we're both interested in is understanding why is this happening, how does this connect to their structure, and how can we put this into a coherent framework for how galaxies are evolving across time. So we also know, and again, this is really driven by HST's great resolution, that if we look back in our census of the universe, that all galaxies are smaller, but in particular, those galaxies that shut down are really surprisingly small. And this doesn't seem to go away. We can't make it go away. They're very small. So that's a really important thing in terms of understanding morphology and star formation and in sort of how star formation is regulated in galaxies. So here you see a factor of 4 to 5 for the same total number of stars. They're much more compact in their size, and as measured by the effective radius. Meanwhile, if we consider just the star-forming galaxies at a similar epoch, these are the progenitors, presumably, of what the most massive things that are going to evolve into quiescent galaxies. They're incredibly dusty. So they are harboring a lot of star formation. This is showing the fraction of obscured star formation in the infrared relative to total as a function of mass. And surprisingly, this doesn't evolve out to a redshift of at least 2.5. And if we focus on massive galaxies, we see that all of them have greater than 90% of their light obscured by dust in terms of what's happening in them. So how do we put this together into a picture of an understanding? So what we really like to do, I guess the questions I wish I understood, and I will tell you I don't yet, so but that's good. That's why we're here. Is how do galaxies form? These are really high-level questions. And what quenches their star formation? What are the physical mechanisms that cause these most massive galaxies in particular to shut down and presumably to stay shut down? So I already ruined it. I can't answer these questions for you, but I think I can provide some slightly more manageable questions that perhaps we could talk about. So when galaxies do quench, do their structures change? And how is this connecting in terms of, we do see, as Mauro showed us, that there is structural evolution in particular, and this is coeval with changes in star formation rate. But are these things actually linked together? How can we understand this question through the context of stellar populations and what we're seeing in terms of the formation histories of galaxies? And then also, I'm really interested in understanding the cold gas reservoirs of quiescent galaxies. I guess I'm generally interested in the gas reservoirs of quiescent galaxies, but cold gas is what is closest to accessible at this point, so I will focus on there in terms of the fuel of star formation. And so in this picture here, I love this diagram in terms of showing that this is not, often a lot of what I'll talk about is really considering something more like a closed box system. And we know galaxies are not closed boxes. We know that they're accreting gas, gases flowing in, gases flowing out. And really, this takes a whole lot of different areas of expertise to really understand a true framework of how this is happening, which I am not going to get close to doing. I'll focus really on the morphology of the innermost region of galaxies and what we see where their light, where they are brightest in terms of surface brightness. So when do galaxies quench? When galaxies quench, do their structures change? And I guess what I really mean to say here, is this a cause and effect, or is it just that there is both things happen to be happening and there's a correlation? So I like to kind of think about this in terms of having a schematic diagram, in terms of how, in particular, massive galaxies are evolving. And so we observe from surveys, especially driven by HST, that we have compact galaxies not long after the Big Bang. And then we see that minor mergers and accretion, we see evidence for this, and they evolve perhaps into a local elliptical. But the question still really remains, how, at these early times, how can we explain the existence of these compact galaxies? And there's a lot of different ideas, I think, especially driven here by theory in terms of how do we explain this. It could be that they just form incredibly early in the universe in a relatively undisturbed dark matter halo, and they're incredibly compact and they just do their thing. Or it could be a sort of a late time event closer to the epoch of quenching, where you have a big burst of star formation, or you're funneling a lot of gas. And certainly there's sort of two camps here, and there's a lot of subtlety in terms of that last point of having a central starburst, of how does that actually happen. Mauro showed this nice diagram showing the specific star formation rate. So these are star forming, these are dead, as a function of the central surface density. Sigma 1, I'm not entirely sure what sigma 1.5 is. It's close to sigma 1, almost the same. So where we see observations, and the idea in these papers, in a series of papers really, both work by Christina Williams, working with Mauro, by Guillermo Barro's work, and I've thought a little bit about this, is maybe perhaps there are sort of two different tracks here in terms of quenching and whether or not this process is happening rapidly or slowly, and perhaps also whether or not one is dominating in the high redshift universe, and perhaps it might be more secular processes are dominating in the low redshift universe. So this is showing a similar plot. Now again, central, so dense, not dense, dead, not dead. And we do definitely see correlations in terms of the properties of galaxies, and on average, the things that are most compact, centrally concentrated, have the lowest specific star formation rates. They have the reddest colors on average. And we do seem to see at least a correlation which doesn't necessarily imply causation, but there's definitely a correlation here between star formation rate and morphology. So now, if we kind of get back to some of the points that Mauro talked about in terms of looking at Redshift 2, I think that there's been sort of some tentative evidence that when you look back in time, that massive quenched galaxies perhaps look diskier, a very scientific term, than what you might expect relative to nearby passive galaxies. And so this is some of the first, I guess one of the papers that came to mind, work led by Arjen van der Waal. And showing here, you can see, gosh, I don't remember which ones. Oh, so the third one down is Sirsic index, and you start to see, in terms of these parameterization of the light profiles, things that are close to exponential, somewhere between exponential and I guess up to somewhere between the something I guess like a lenticular. And so this is sort of tentative evidence. And so I guess I would pose the question, is this good enough? Should we be using Sirsic index to say that we're seeing disks at high redshift? And I'll get back to this. Or using axis ratios. Certainly it's a good tool, but maybe asking the question of what's the best tool. Certainly this is what we have, so you use what you have always. But maybe moving forward, what would we need to do a better job? And this is a plot shown also by Mauro, by Drew Newman, not Norman. Okay. I think he'd be okay with it. And showing, this is basically the degree of angular momentum. So lots of angular momentum, not a lot, and then ellipticity. And so what you see when you look at high redshift dead galaxies, the first tentative evidence we have from lensed galaxies is that these things they have a lot of angular momentum. And so this sort of gets hairy in terms of saying, oh, well, there's disks. We're seeing disks, dead disks. Are they really disks? I don't know. They have a lot of rotation. I don't necessarily have an answer to this, but I do think that this is the right way to go of how you would actually measure this dynamically. These are the sorts of measurements that you need. This is also, in terms of this picture here, there's been a lot of other papers, earlier papers also actually from my thesis survey, Van Dokkum 2010 also looked at this, where you can look at the surface density profiles and how they're evolving with redshift. And we see this very gradual buildup of the light profiles. And it's not really happening in the inner regions, it's happening in the outer regions, which kind of made me wonder, maybe this is also, since we have pretty well observed that we see this happening statistically, explaining some of the evolution that you're seeing in Gini, I think would be the right coefficient. Oops, sorry, teaser. I would say if we want to understand the formation pathways, and that's really what I want to get to, I also want to understand quenching. I'm not sure how accessible that would be. Maybe they come hand in hand. But how do these galaxies form? I think we need, the tools that we need moving forward is actually resolving the stellar populations and trying to get an understanding of their picture, their formation history, and then also looking at dynamics. And neither of these things are easy because these things are barely resolved with Hubble, especially the most compact things. It requires technology that we don't really have accessible to us yet. So I show up here. So this is from Erica Nelson's picture, but using this as a demonstration, picture. This picture is from work led by Erica Nelson. And this idea of how do we take these larger star-forming galaxies that we observe? They seem to go through a very dusty, compact, potentially. Maybe they don't, but maybe they go through a very dusty, compact phase. And perhaps they come out on the other end as what we observe as a red and dead quiescent galaxy with not too much dust. How do they form? How do they quench? This is the half-light radius here. So this is showing angular resolution as a function of wavelength for some current facilities and future facilities. This is the half-light radius at a redshift of 2. And so what you can see is HST is just doing the job. Like, it's just good enough. We can sort of mostly resolve these galaxies, but it's really borderline here. If you want to understand gradients, that's barely resolving is not good enough. You need to really have many pixels within the half-light radius. JWST is going to extend and provide amazing spectroscopic capabilities, but it's not going to be a huge leap in terms of resolution. It's going to, again, open a whole new window. And I should get back to this point. But it's really not going to change things in terms of angular resolution for our understanding. I think the game changers here are going to be ELTs, in the infrared, which is particularly critical for cosmic noon, because that's where all our rest frame optical features are. ALMA is going to continue to be important here. And then if we had something like Keck in space, bigger than Keck in space, like LUVOIR. So in this timeline, what's our wish list? What's our what do we hope for in the future? So first you'll notice that I have HST living forever, as well as ALMA. Maybe it's slightly optimistic. If we look into the 2020s and into the 2030s, we have a lot of exciting technology that's coming, hopefully. Certainly, I guess I've listed things, well, nothing is certain, so I don't know. But certainly, we're all hopeful that JWST will be launching soon. And then we'll also get into this era of lots of competition in terms of the 30-meter class era of telescopes. So where do those put us? Right, those are the things that are going to open up these new windows in terms of actually resolving down to individual giant star-forming complex of galaxies across all of time. And this is really going to change our understanding of the morphologies of galaxies. But what can we do now? So this is showing, oh, it's going. Is it going? Damn, it's going. Okay, hold on, go back. No, I can't. Okay. Ruined my punchline. So this is showing a simulation of a galaxy and changing the resolution. I'm making my telescope bigger and bigger. And I don't know if it's going to let me go back. I think it finished. I was going from Hubble to LUVOIR, but it went too quick. Okay. Well, if you were to look at that original Hubble image and just, by eye classify that galaxy, to me, it kind of looks like an edge-on disk with a bulge. Maybe close to lenticular, but pretty disky. When we actually get much better resolution, you can see that this looks nothing like an edge-on disk. It's very clumpy, small regions of giant complexes of star formation. But because we don't have the angular resolution, to us it looks very different. And so if I go, I think I'm going to add next my, is it doing it? What's going on? Hold on. Poorly planned. So this is a picture, something like what we would see with LUVOIR. This is my LEGO person now by comparison. I'm roughly the same height, 5'6", 5'7", as my LEGO person and close to about one segment of LUVOIR. Whereas when HST was here, right, it was just a little bit bigger than me. That was the whole mirror. So now that's just one segment. This is the simulations are based on actual observations of a gravitationally lensed galaxy. This is the source plane reconstruction of this galaxy. It's at redshift 2.5. This is what it looks like on the sky, a pretty spectacular, one of the brightest arcs that we have in our night sky. And I guess I show this as a lesson that right now we measure morphologies. And I wonder a little bit how our picture is going to change when we have much better angular resolution with bigger telescopes, even 30-meter class telescopes. So, that's where we're going to enter the era where we're probing something 50 to 100 parsecs on all scales. Well, even better for nearby galaxies. And then we can start to spatially resolve star formation, emission line, age, metallicity, dust, and figure out how they came to be. And it just sort of makes me wonder, but not enough that I don't keep working. But it motivates why I'm really lately interested in also using gravitational lensing as a tool to sort of do science of the next generation, but now. Modulo, we have to have a lens model, and that's a big if. But with that, we can sort of try to understand at much higher spatial resolution galaxies. And so this is showing an illustration. So first, Mo was here yesterday, my graduate student. So for those of you who were able to listen to his talk, this is related to his work. But this is at the native pixel scale of HST. JWST at the same wavelength is a bigger telescope, will do better. But when we have lensing and a reconstruction, you're really getting into ELT science, and we can start to see differences. For example, here, there's actually two little clumps in this lens reconstruction at the UV wavelengths that you otherwise would absolutely not see. So Mo is leading a new HST survey, which he, for those of you who are here, talked about yesterday. This is showing the size mass diagram. In the background are the sort of general statistical population from the 3D HST survey, and then these are our targets. And so these are all strong gravitational lensed dead quiescent galaxies. They're ranging from a redshift of 1.5 to 3, roughly speaking. And So this will be incoming. Mo's going to be leading the HST survey, where we're going to get some of the deepest GRISM spectroscopy that will exist in the archive of all of our targets. And then we also have an ALMA program that I'll talk about shortly, and both in terms of understanding the gas properties of these galaxies. So Mo's work is in spatially resolving. So leveraging the fact that some of these, one of them has a magnification of 30. So it's amplified, not only is the light amplified, but it's stretched. And so you have sort of like looking with your cosmic microscope to see and peer inside these galaxies and see it with much better angular resolution. This is showing the work he talked about yesterday in our pilot study, which turns out to be a really challenging galaxy to understand with a very complex star formation history, and it's very old. The older things are, even in the early universe, the harder they are to understand in terms of the signatures that we're able to see. But this is another target that I'll talk about that has, this is just one orbit, so we haven't yet gotten our new data, but we'll have much deeper data. But from this already, you can kind of see by eye. Do you guys see the Balmer lines, right? We can actually see very clearly very strong Balmer lines. And unsurprisingly, this is a post-starburst galaxy, about 500 million years, where you have these very strong absorption lines. So stay tuned for work on this. This is the photo gallery of the Requiem survey. It's a slightly more generous version. Not all of these are going to be in the HST program, but this includes the full sample that we have, and some of them are being observed through ALMA, and some with HST. And what I wanted to, so you can see here, this is the image on sky, so you can see some of these great, look at that monster. Whoa, right? It's huge. This is the source plane reconstruction. These two, we don't yet have a lens model. That will come with the HST data. So, in spirit of the ALMA deadline today, I've been thinking a lot about gas properties. And one thing that we really is not well understood is how much gas do these massive dead galaxies have, and how does this factor into their structural evolution as well as quenching. This is showing some compilation. These are sort of the typical taconiidal, crazy high star-forming galaxies, lots of big gas reservoirs. And then this is kind of what we have for dead things. So you see a lot of arrows pointing down because pretty much most things are not detected. So we have upper limits that suggest that they have small gas reservoirs. We don't actually know how much, on the order of 10% or less. So I was excited to get some data from ALMA a week ago. It's a cruel gift, a week before a deadline. Before I get into that, so this is from stacking. The Gobet et al. Are some beautiful results showing stacking. And if you just had a gas depletion time of something like 2 to 3 billion years, it's consistent with this other upper limit detection, and this is how you would evolve in redshift in terms of how you use up and deplete your molecular gas reservoir. This is showing our detection. This is for that MAX 2129, where I showed you the one orbit of data, so we're getting much deeper data. And we have one of the first, I think the highest redshift detection. I'm not really, I think, as far as I understand. It's constrained to be a gas fraction of 3%, plus or minus 0.3, 0.4. So it's a very tight constraint. It's a 9 sigma detection with dust continuum. This was the CO for the same target where we had an upper limit. And this is the detection with dust continuum. And so I haven't fully thought this through. What does this mean? I don't know, but I want to think about this a lot and try to understand how this fits into our picture. I did want to show very quickly, this is some results from Legacy at a redshift of 0.7. And these are, again, upper limits for a lot of these galaxies. And this is, if I did my calculations correctly last night, where this target sits way down here, which is actually somewhat consistent with gross extrapolations of star-forming galaxies. So I don't know, maybe the timescales work out right. I don't know. The universe is usually not that generous. I'm also really excited to try to look at these targets with JWST with that IFU. That's going to be pretty amazing with that high spectral resolution. And then I wanted to leave by saying, what do we need to understand these things? I think we need an order of magnitude improvement in resolution. We need improved sensitivity and instrumentation. And we need to continue, which we already have, but continue having this broad wavelength coverage of multi-wavelength view of galaxies. So I think when we have this, so if we have things, this is showing a diagram. This is the 3 spaxels of the IFU for a redshift 2 galaxy. And then this is showing something with like TMT, so those are all individual spaxels with a 30-meter class telescope. So you can start to see, in terms of decades, the direction of hopefully where we're going. But we're pushing towards, we can do now with gravitational lensing, resolving individual star-forming regions, and soon with 30-meter telescopes, we can do this for all galaxies, right? And so we'll actually have a, I don't know, maybe our picture will be the same. Maybe it won't. I don't know. I don't have that answer. Maybe you guys can tell me. But we can also, really importantly, figure out the dynamics, and returning to what you were saying, like we can actually, we'll have the tools and the instrumentation to actually properly measure dynamics, as opposed to basing things on light profiles where it's, we want deeper, higher resolution imaging. So, and then I always like to think about, okay, when we have 30-meter class telescopes, what happens if you point those at gravitationally lensed galaxies? I don't know, but that would be crazy too, right? So they're always going to continue to lead the field, so we should also always do these large, both are important, large statistical galaxy surveys and using gravitational lensing as a tool to push forward. Thank you. How do I, should I take this off? Or do we I think if you touch it, usually it does weird things, so.
Yes? I sort of had a clarification question. So if you were to go back to that picture that you had from Eric and Nelson's the compact galaxy in the middle, and so the question is, what does...
Oh gosh, you're going to make me go through the, I can't go through that, well, hold on, no, I can do it this way. Okay.
Starburst galaxy, a lot of the light, or most of the light, comes out in the infrared. And the starburst is typically restricted to some region around the nucleus. Not all, but so if I take a starburst galaxy like nearby one, like M83 or NGC 253, then I might not say that that galaxy is more compact than a typical spiral, but the infrared light, and if the infrared light is a significant fraction of the total light, when I did a half-light radius, I would say, well, that looks like it's compact in that definition. So what does this mean?
So let me unpack a few of the things there. So I guess it depends, first of all, how do you define the size of a galaxy?
Well, that's what I'm asking.
And usually we do that in the rest optical, so you're not going to be dominated by dust. It's actually the opposite could be the problem, right, where you're losing optical light because of dust, and so it might not even look as compact as you might think, right? Erica has actually led work on this in terms of the light profiles and the centers of these galaxies, and whether or not we are missing, similar to the submillimeter galaxies, you see that they're very compact, intense bursts that are very compact. Normally, I guess we sort of avoid that problem because we try to look at rest optical features, and so it's not going to, I don't think it would go in that direction.
That's what I'm saying, but it just looks like you start off with this thing on the left, it's blue, and then it goes red, and are you using the same light?
Oh. Well, that's, so this is, oh, Sparky, that's Sparky, isn't it?
So you're saying that
So I guess the way I view this is that we have big things, and they turn into small things, and it's really hard to lose that angular momentum. And if you look at very, very deep imaging of dead things, we don't think we're missing a low surface brightness component. And so they seem to fundamentally change their structure, maybe. If these are two different things, right? Like that's not the same as that. So I don't know if that's going to evolve into that. Just statistically speaking, we have a whole lot of those things, and we have these, and yeah.
Would the other speaker care to chime in
Yeah.
on the matter of structural transformations? Do they actually transform?
So, I think they do. They do transform somehow. We still don't fully. What Kate is showing here is not obviously the same objects. Presumably, it's observed using the same bands. If I don't know which data you're showing here, but if this is some interesting images, the color composite is very likely obtained using the same passbands. clearly, the star-forming one, the light is dominated by young massive stars. The light-to-right mass ratios of an O star is 10 to the 6 times one of a G star. So obviously, what you see in there is the light of O and B stars. What you see there is very likely the light of J, G, and K stars, right? Now, it's
not in the starburst galaxy. It's the same mass, same population of massive stars. It just comes out in the infrared.
no. Are you showing HST data here?
That is HSD data.
So
It's-
if it is
606, 160.
the same survey with the same filters, the same passband, you are seeing a star-forming galaxies and the red and dead galaxy, presumably the same redshifts. I don't know what you have selected.
Yeah, you
right?
keep looking at me, but I'm
So-
pretty sure it's around the same redshift. This is, yeah.
So that is essentially non-forming stars anymore. If you look at the spectrum, it looks to you like an elliptical galaxy, or that one looks to you like line emission dominate the spectrum. Now, do they shrink? If you remember the pistol diagram that she showed, that I showed, we have never been able to follow the same galaxies during the evolution, but I don't know if they shrink. I don't see how they shrink. How do you convince the non-dissipative components like stars to shrink? But they certainly develop a central, very massive source. But what is it? Let me show you some tricky plot. Actually, can you put out my plot? You have it in the Dropbox.
Oh, yeah.
So we don't have to exchange computers.
Yeah.
So this is exactly what Kate was saying. They don't seem to have an extended surface brightness halo. So this is tricky. I don't.
Which pot do you want?
This is it. There's a stack. Keep scrolling. This one. So what you see here.
Hold on.
as soon as-
You're going to see when I figure out how to play.
So this basically drives the point that Kate was telling you. What you see in red here is the stack of some 98, I don't remember, it's written somewhere. Anyway, of these red nuggets, it was the plot on the right of the 3 that she showed. Some 90 of them here entered this stack. This red line here is the best surface profile, okay? Together with the light profile of modern elliptical galaxies. Courtesy of John Cormandy gave this to us, transformed into mass density using the mass to light ratio that they calculated. So as you can see, well, first of all, the first thing to notice is that the high redshift, this is Hubble losing steam. This is the fact Hubble, as high resolution
It's
as it's
almost 30
capable
years
of,
old.
cannot follow the innermost regions of galaxies of redshift 2, right? But the best surface profile fit, caution now. Today, if you fit a local galaxy with a surface profile, there is no galaxy that can be fit by one surface profile only. There are regions where you can use one surface profile, but different regions have different fit. That said, the extrapolation of this part could very well be, so this is a cuspy galaxy. This is a cuspy local galaxy. So cuspy local galaxies can be pretty dense, right? These are core galaxies. What is interesting, this is the point that Kate was making, the high redshift galaxies don't have the skirts. They're really compact, like a lot compact. So I don't know how they lose their halo. I mean, I don't see how they can lose it, but they don't have it, the halo. Elliptical galaxies today have a lot of low surface brightness outer regions. The high redshift ones, of course, we know Hubble is not very sensitive to low surface brightness light.
There's
we're talking
been
of
some work on
90
it, though.
galaxies here stacked together.
There's
Yeah.
a cosmological dimming of a factor of 60.
Yep, 1 plus e to the
So
16th
so
power
there's
third
work
power,
going
the
down
third
to like
power.
29th.
They don't know the energy.
What's surface
Yeah.
brightness?
So-
This is a stack, yeah.
So there's, if you stack, going down to very, very low surface brightness limits of like, this came like circa 2008 is like when we're like, no, we don't believe this. They have to have a halo. It doesn't seem statistically like it is. I mean, I shouldn't, right, this is stacking, so you can always do better in terms of getting more sensitive and doing it for individual, but
Yeah, there's a
on average, they don't have low
plus one
halos.
The third power, not
Oh,
no, physical is the fourth. But the CCD within the passbands,
Yeah.
where there is low energy or high energy, so you recover 1 plus e effect. With if you use a CCD.
Okay,
CCD, they don't, it's not the energy of the electron, the photons, when they raise the electron.
let's give these guys a hand, and then we can chat over coffee. Sound good? Thanks, guys. I was like, well, we should wrap up so that people can take off, but yeah.
If you have any energy counter, yes.
How do I turn it on?
Regardless of it.